I'm delighted that we're going to hear about Rees algebras of ideals and 2x2 minors, among my favorite subjects, from Claudia Polini, who's a professor at Notre Dame University and an organizer of many, many conferences at which many of us been. Speaking to us from her sun porch, if I'm not mistaken.
Yes, yes.
Okay, with many co-authors. So Claudia, go ahead.
Okay,
Please.
so thank you. So first of all, I would like very much to thank you all, the organizers of this wonderful seminars. And so far, the seminars I have assisted to, all of them, they were fantastic. So I hope I do a decent job and just to make honor to you guys. And thank you, because this is such a difficult time. I'm used to travel everywhere, and now I'm home, and it feels like a prison to be home. So, you know, my sun porch is nice, but it would be much nicer to be somewhere else. But anyway, so this seminar gives us still the idea of community, and that community of algebra is a strong community, and that's very important. So today I'm going to talk about, as you mentioned, this algebra of ideals generated by 2x2 minors. And this is a joint work with Algebras, Dufresne, Puli, Gorla, Lin, and Swanson. I will also mention the work with Wang, Perlman, Raiku, and Sammartano. But I mainly focus on the work with these 6 girls. So these are 6 women. And this work was started at WICA, which was organized by Karen Smith, Sandra Spiro, Firena Swanson, and Emily Witt last fall in Banff. So this talk is going to be made up of 3 parts. And the first 2 parts are not my work, are supposed, except for when I cite the work of Wang, Perlman, Raiku, and Sammartano, which I am part of it. But most of it is general stuff. And then I'll go to the last part, which is the work with the girls. So we first talk about Rees rings of ideal that are generated by maximal minor of generic matrices. And then we generalize it in 2 directions. The first direction is non-maximal minors of generic matrices, and 2x2 actually minor. And the second one is maximal minor of matrices which are not generic, more precisely sparse matrices. Now, we are all familiar with projective space. After projective space, perhaps the most important variety is the Grassmannian. And as one can read in Bruns and Vetter, while projective space gives a geometric structure to the set of one-dimensional subspace of a vector space, a Grassmannian variety does this for the set of m-dimensional subspaces. So we want to parameterize the m-dimensional subspaces of a vector space V. So we fix a K vector space V of dimension n, and with a fixed basis, okay? And then we take, we fix an M is between 1 and n, and we consider the set of all W, and the W are subspaces of V of the fixed dimension M, okay? So once we fix a basis of W, we can immediately associate to W a matrix, which is, we call it M, is an m by n matrix. And how do we associate it? Each row of M consists of the coordinates of the basis element of W with respect to the fixed basis that we had in V. Now, unfortunately, this association depends on the chosen basis that you had of W, the basis you chose of W. If we want something to have an object associated to W that does not depend on the basis you choose, but only on W, we have to actually take the maximal minors of M. Up to a fixed scalar, they depend only on W. So what we do, we actually have, we can associate to W a well-defined point in projective space. This map that associates to all the subset a point in projective space is called the Plucker map and is injective. Hence, we can define the following map actually, not a map, a rational map. We take X to be an m by n matrix of variables. I'll call them Xij. And then I consider delta 1 delta n choose m, the maximal minors of X. And I consider the map, the rational map between projective spaces, which is defined by this maximal minors. The closed image of this rational map is what we call the Grassmannian variety. And this Grassmannian would actually comes with this natural embedding in projective space, which we call the Plucker embedding. Notice that, first of all, this delta 1, this maximal minor, parameterize the Grassmannian variety, and often they're actually called Plucker coordinates, okay? And also the closure of the Grassmannian consists exactly of all the m-dimensional subspaces of V, because that's what the Grassmannian does, parameterizes this, what we wanted, the subspace of W. In theory, this depends on the fixed basis that I had of V at the beginning. But however, all the different embeddings that you get when you change a basis of V are all projective equivalent. So it's really independent of the choice of basis. Now, I want to investigate the homogeneous coordinate ring of the Grassmannian. So for this, I call IM the ideal generated by the maximal minor. What is the homogeneous coordinate ring of the Grassmannian? Is the algebra generated by the minors over the field K. Remember, V was a K vector space, any field K. And this is a subalgebra of the polynomial ring over K generated by the Xij, the entries of my matrix X. And I call this algebra the Plucker algebra. And I also denote it with FIM. Okay, and we'll see why after I call it FIM. Okay? Now, the Grassmannian has been widely studied. So let's see some of its properties that are going to be important for us. But first of all, the Grassmannian is smooth, which means it's non-singular, of dimension m times n minus n. And this can be easily seen because the Grassmannian is covered by affine spaces of that dimension. How do you see it, for example? You take any minor, which is at least one is different from 0, and then when you invert it, you get the rest of the matrix is completely free, and the rest of the matrix exactly as size m times n minus n. The fact that the Grassmannian is smooth means that the Plucker algebra is actually regular on the puncture spectrum. But one can show also that the Plucker algebra is Coli. So since it's regular on the puncture spectrum, is also normal. Furthermore, actually the Plucker algebra is even factorial. And now being a K algebra of, as a canonical module, but then if it has a canonical module and it's Coli and is a UFT, then it's Goresten. Okay, and the canonical module is actually isomorphic to a principal ideal. And this principal ideal lives in positive degrees, which means that the A invariant is actually negative. So the Plucker algebra has either rational singularity in characteristic 0, or if you want is F rational in characteristic P. Another way to see that is actually a rational singularity in characteristic 0 is because the special linear group, SLM, acts on the rows of the matrix via a left multiplication and leaves invariant all the maximal minors. But it turns out that the Plucker algebra is actually the full ring of invariants. And since the special linear group is a linearly reductive group by Buteau, it has rational singularity. Now, this was already pointed out, if you remember, in an URAG lecture. Now, we want to write the Plucker algebra as a quotient of a polynomial ring, okay? So, in particular, we want to understand its defining ideal. So, what are the algebraic relations among the maximal minor? We consider a new polynomial ring in new variable, ti. Each ti corresponds to one of the maximal minor, delta I, okay? And we map subjectively this new polynomial ring, I'll call it T, to the Plucker algebra, okay? And the defining ideal is exactly the kernel of this map. And in general, it's a very difficult problem in commutative algebra, algebraic geometry, and elimination theory to determine what is the defining ideal of a variety defined parametrically. And it's a problem that is important even in applied mathematics, most notably in geometric modeling. And now, in the case of the Plücker algebra, this problem was already studied by Plücker over 150 years ago, and then by Grassmann. That's why the name Grassmannian and Plücker. And the algebraic relations are simply the Plücker relation. They are quadratic relation. Okay, I'm going to explain actually the Plücker relation in the case of that I'm interested in. So I'm going to explain them in the case of a 2 by n, of a matrix which is size 2 by n. Okay, so to explain the Plücker relation in that case, we need to choose 4 columns of the matrix. And choosing 4 columns of the matrix just means choosing 4 indices, I, J, K, L, M, I, J, K, L, all distant between 1 and n. Okay, and I can assume they're all increasing. Now, what are these Plücker relations? You consider the minor, every 2 by 2 minor, remember here the maximal minor are 2 by 2 minor. Every 2 by 2 minor is defined when you choose 2 columns. So I choose 2 columns, I and j, and I get the minor. I denote the minor this way. And then there are 2 columns left. I'll take the minor in the complementary k and l left over. And then I take I and k, and I take the complementary jl. And then I take I and L, and I take the complementary JK. How can you see that these are relations? But you take your matrix X, you double it up, you get a 4 by n matrix, whose 4 by 4 minor are all 0. By computing the 4 by 4 minor using Laplace expansion of complementary minors, we get the relation. So from this relation, how do we get actually a generator of the kernel of this map? But we have to, in the place of the minor ij, put the corresponding variable t that corresponds to it, that is mapped to it. And in this case, I denote the variable with 2 indices to recall that this is the variable that is corresponding to the minor. And since they're 2 by 2 minor, I need only the column I and j to select it. Okay? And this is the Plücker relation I, j, k, l that depends on this 4 set of indices. And you can do it for any set of indices. If you put it all together, you get what's called the Plücker ideal, which is the defining ideal of the Plücker algebra. Now, this will come back also remember this P because I'll recall it to you also in the last part of the talk. Now, there is another important algebra associated to the map and the rational map. And this important algebra is called the Rees algebra, is the homogeneous coordinate ring of the graph of F. So this is the algebra generated over R by delta 1t and delta n choose nt, okay, by the maximal minor time t. Is a subalgebra of the polynomial ring in one variable t over the ring R. And I denote it with RIM because it's the Rees algebra of IM, okay, of the ideal of maximal minor. Now the graph always tells us more information than the image on a map. So in this sense, and not only it encodes the image. So we can expect that the Rees algebra will encode the special fiber and will give us information, the Plücker algebra, and will give us information about the Plücker algebra. What is the relation? That you know that the graph is a subvariety of the product of projective space, the product of the source and the target, and you can always project on the second component, and this projection, you know, at the level of the graph is equivalent to the projection of the graph into the image, okay? Which is, as I said, embedded with the Plücker embedding. And now this corresponds to the diagram, algebraically, of Rees algebra and Plücker algebra. How? The coordinate ring of this product of projective space is the tensor product of the ring T that we already introduced and R. And we call this ring S. It's the polynomial ring over K in 2 sets of variables, the original X and the new T's. And this S map homomorphically, and that corresponds to this inclusion, to the Rees algebra. the defining ideal of the Rees algebra is the kernel, we call it J, of this surjection. The projection in the second component corresponds to the inclusion of T into S, and the inclusion of the embedding of the Grassmannian inside this projective space corresponds to the surjection of T to the Plucker algebra that we already talked about, and its defining ideal is P, as we already said. And the map now that we consider is the map that sends that Ti to delta T. In this version of the Plucker algebra, we think of the Plucker algebra, which is isomorphic, as the algebra generated over K, but not delta I, but delta IT, but is isomorphic, so it doesn't matter. The Rees algebra is bigraded, you know, because we can give, because this is a product of projective space, we can give degree to the X is 1, 0, to degree to the T 0, 1. And then this is a bigraded ring, and this is an epimorphic image, so inherits the bigrading. So J is a bihomogeneous ideal. And this is gonna be very important actually, okay? Now we step back and I talk about actual general situation. The green represents the general. You can construct the Rees algebra much more in generality for every ideal in the Noetherian ring, but I'm gonna do it for this talk just for an ideal generated by form of the same degree. I can call them F1, Fs inside the polynomial ring R. And the Rees algebra, as we said, is the subalgebra of RT generated by IT. So is R in degree 0, IT in degree 1, I square T square in degree 2, and I denote it with RI, okay? And inside it, we said before, the Plucker algebra was sitting. The Plucker algebra is just a special fiber ring. The special fiber ring is the algebra generated by F1T, FST over K, and it always sits inside the Rees algebra in the case in which F1, Fs are form of the same degree. But we can also get the special fiber ring as a projection from the Rees algebra, just killing the x's, sending the x's to 0. So the special fiber ring is an algebra retract, which will be very important. The special fiber ring is, if you want, the component of the Rees algebra in degree 0 star. And here we really use very much the grading, okay? Blow-up algebras, so these algebra actually are called blow-up algebras, okay? And they're very, very important. They play a role in resolution of singularity, but they're also, as I said, relevant in the study of an ideal and all its power, and above all in the asymptotic properties of ideal. They're also the natural environment where integral dependence is defined. I could talk for an hour about their importance, but I have lots of stuff to say. So let's go back to the Rees algebra maximal minor. Now, for the Rees algebra maximal minor, also that's very much studied, and in 83, Eisenbach and Juneke prove that the Rees algebra of maximal minor is a graded Hodge algebra, or as it's called over K, or as it's called an algebra with straightening law, on a wonderful poset, and in particular is Comecoli. Already Hodge in 1943 had shown that the Plucker algebra had such structure over the poset of the maximal minors. Obviously, he didn't call it Hodge algebra. The name Hodge was given by the Concini Eisenbach Procesi in 82. But now, going back to our Rees algebra, as Grifo pointed out, the symbolic power of the ideal of maximal minor are all equal to the power. In terms of Rees algebra, because I told you the Rees algebra reads the power, means that the symbolic Rees algebra is equal to the Rees algebra. This tells you in particular, and this was proven by Chung in 79, but it could be proven, and it was proven also in this paper, with the Comecoliness immediately, just bounding the analytic spread locally, okay? The analytic spread is the dimension of the special fiber ring. And actually, once you get this equality, then you get immediately the equality of the integral closure, and because they're squeezed in between. And this is equivalent to the fact that the Rees algebra is normal. Again, property of the Rees algebra tell you stuff about the ideal and its powers. Now, I want to, many more things. There are many, many papers about the special fiber and the Rees ring, so special fiber ring and the Rees ring of determinantal ideals. So I cannot tell all the property. I have few time. So I will just mention that, for example, the divisor class group, the canonical class have been investigated, and there was the work of Herzog Vasconcelos, the work of Bruns, Simis, Chung, using again the Hodge structure that was defined by Heisenberg and Uneke. And when we look at, for example, another thing I should mention, with invariant theory, you can also show that there is algebra as rational singularity, like we said for the Plucker algebra in characteristic 0, or is F rational in characteristic P. Now, I want to go to the defining equation, also to the defining ideal of the Rees algebra, like I showed the one of the Plucker algebra. So I ask, what is J? But J always contains P, okay? But is made of, there is no just P, is not equal just to P. So what else is in J? But let's step back, do the green part, and do it in general. So in general, this P corresponds to the ideal J0 star, which sits in J. And J0 star means degree x0 and star is any degree in the T's, is the defining ideal of the special fiber in general. But inside J, there is also J, the component J star 1, means you fix the degree of the T degree 1, and the X is any degree. And this one is actually obtained by the syzygy of I, and they are exactly the generator of the symmetric algebra. A classical way to study the Rees algebra is via the projection of the symmetric algebra into it. There is always this canonical epimorphism, but just by the universal property defining the symmetric algebra. And why would we look at the symmetric algebra? Because the symmetric algebra is much easier understood in terms of generator relation. It's just written as S was the polynomial ring in the X's and the T, modulo what we call L, okay? Which is called L because it's called the linear ideal. So let me step back and remind you that I already said that the symmetric algebra was generated, the defining ideal was generated by J star 1. So now I tell you is L this ideal, so I want to describe it. L is obtained from a presentation matrix of I. In which way is obtained from a presentation matrix of I? So I take phi, and I take the vector of the T, and I multiply by phi, okay? And I take the ideal generated by this, which are called the linear equation because they are linear in T. To be concrete, let me do the example of the maximal minor. So let's go back to the maximal minor. In the case of the maximal minor, we always have a phi presenting the maximal minor because we know that the maximal minor are resolved by the Egon-Norcott complex. So to determine the linear equation, we just need the Egon-Norcott relation. So how do I get the Egon-Norcott relation? Remember, my matrix was a m by n matrix. I append to the bottom any row of the matrix X, and now it's an m plus 1 times n matrix. I take the maximal minor of that, the m plus 1 minor. Each one of them will give me a relation, and this relation will give rise to the syzygy that generate L. How do I do that? I'll show it in the case of the 2 by n matrix. In the case of the 2 by n matrix, I only have 2 rows to play with. So I call the index U for 1 and 2, and m is 2, so m plus 1 is 3. So I have to take the 3 by 3 minors. So I need to select 3 indices, I, J, K, from 1 to n. And they will correspond to a 3 by 3 minor. And then, yes. And I will expand to compute the 3 by 3 minor respect to the row I added. So I get XUI times the minor JK, minor XUJ, XUJ times the minor IK, plus XUK times the minor ij. So this is the relation, because the 3 by 3 minor are 0. And how do I get from here the syzygy? But I have to substitute, I have to replace the minor, in this case the 2 by 2 minor, with the basis element corresponding to it. And these basis elements are the variable t in the polynomial ring S. So we replace it with the base element tjk, because it corresponds to the minor jk. And this linear equation, I'll call it L uijk. I'll take it for every uijk, and I get an ideal L, my linear ideal. Okay, so now let's go back to, again, the general case and give you actually some definition. We study, as I said, classically, there is algebra via the symmetric algebra. And the best case scenario is when they are isomorphic. When they are isomorphic, it means that, actually this should be if and only if, this first part, J is L. So we know already that this algebra is also just defined by L. In this case, the special fiber ring is a polynomial ring, and the ideal I is called of linear type. Linear because it's defined by the linear equation. And if this is not the case, the next best case scenario is when J is defined by the two components I talked about, the linear equation and the component J0 star, which was the defining ideal of the special fiber ring. So I, in this case, is called of fiber type. The last definition is the relation type, which will be very important for us. The relation type of an ideal, called also the R-type of I, is the highest degree, T degree, of a minimal homogeneous generator of I, of J, of the defining ideal of the Rees ring. And for example, if I is linear type, the relation type is 1, obviously, because the equations are just linear in the T. So now let's go back to the Rees algebra maximal minor. The Rees algebra maximal minor is always of fiber type. Actually, even when m is equal 1, or n is m plus 1, or less than equal than m plus 1, in that case is of linear type, but linear type is always fiber type. So the Rees algebra of the maximal minor is simply the polynomial ring S modulo the ideal generated by L and P, the Lucas ideal. And this can be seen by the work of Eisenbach, of Uneke, because you can use the Hodge structure, because the straightening relation determine actually all the possible relation. In particular, the relation type of the ideal of maximal minor is less than equal than 2, okay? Less than equal because if it's linear type is actually 1 when it's linear type. Now I come to the part of the talk, which is a little harder, just 5 minutes when I go back to general part. So what's happened for non-maximal minor, okay? For non-maximal minor, a lot of work has been done. So I can assume that T is bigger than 1 and is less than M, because for T equal 1, I already said is trivial, and strictly less than M because for T equal M, we talked about it. So IT denotes the ideal of T by T minors, okay? As I said, much less is known, though many, many papers were written about it. I want to cite just the paper of Bruns in 91, Bruns Conca in 98 and in 2001, and the seminal paper of Bruns Conca Barbaro in 2013. For example, Bruns showed that the Rees algebra has rational singularity in characteristic 0 using variant theory. So its particular is normal in Come. Then Bruns, and he gave an example that actually the Rees algebra is not Come for exceptional characteristic. And in characteristic P, Bruns and Conca using Sagby bases, and we'll talk about Sagby bases next, okay? They show actually that it's Come except the exceptional characteristic. And then they investigate the canonical class, the divisor class group, the symbolic Rees algebra, and they used a lot, lots of the property of this algebra. But still, open is the question, what are the defining ideals of the special fiber ring of the T by T minor, of the ideal generated by the T by T minor, and there is algebra generated by the T by T minor. As said in the seminal paper of Bruns, Conca, Barbaro, maybe the reason is due to representation theory, because for maximal minor, each graded component of the Plucker algebra is an irreducible GLV cross GLW representation. And this is not true for arbitrary T. In the paper, actually, of Bruns, Conca, Barbaro, they conjecture that the special fiber ring of the ideal IT is generated by quadratic, not just Plucker, and cubic relation. And so this is their conjecture that I state here. And they exhibit such a relation even between the T minors. And they express them in terms of GL irreducible representation. They also prove that the 2 by 2 minors and the 3 by 3 minors, okay, for the case of 2 by 2 minor and 3 by 3 minor, there are no further quadratics and cubic relations. And actually, even if you go to the Tor in degree 4, is 0. So, you know, if there are any relation, they say they have to be in degree 5, 6, or over, okay? Now, we conjecture that the ideal of T by T minor is of fiber type. Remember that fiber type means that the ideal defining the Rees ring is obtained by the ideal defining the special fiber ring. So if you couple it with the conjecture of Bruns, Conca, Barbaro, you immediately get that the relation type, a third conjecture, but the relation type of the maximal of the T by T minor, not maximal, is actually even for the maximal is less than or equal than 2, is less than or equal than 3. Okay, now I want to just mention the work with Wang, Perman, Raico, and San Martano that is in characteristic 0. And what we prove there, we prove that first of all, the defining ideal of the special fiber for 2 by 2 minor are actually generated, the defining ideal is generated in degree 2 and 3, exactly by the relations, this should be relation, should be an S, described in Bruns, Conca, Barbaro. And we use representation theory for this. About the conjecture of fiber type, okay, we actually prove that to check that the ideal of 2 by 2 minor is a fiber type for any generic M by N matrix is equivalent to check that it is a fiber type for a generic M times M plus 2 matrix. In particular, if you use Macaulay 2, you can prove that if you look at the ideal defined by the 2 by 2 minor of a 3 by N matrix, this ideal is a fiber type. And in particular, it's Rees ring, because of our first result, is well understood in terms of generators and relation. Okay, now I would like to go to the second part of the talk, okay? And then we'll take a break, it will be shorter, we'll take a break and then I'll have the third part. There is algebra, okay, we are considering are subalgebras of polynomial rings. And one way to study such algebras are subalgebra analog, okay, of Gnobber bases for ideals or Sagby bases. They were introduced by Robbiano and Swigler and independently by Kapur-Madler, I think at the end of, maybe in the 90s and at the beginning of the 90s. And A, for us now, is a finitely generated K subalgebra of the polynomial ring over K, generated by some variable called them x1, xn. We fix a term order on the polynomial ring. A term order is just a total order on the set of monomials of R. And we associated to A, to the algebra A monomial algebra, the initial algebra of A, respect to tau. And this is the algebra generated by the initial term of F for every F in A over K. Okay? This is the analog to what we do for ideals when we pass to the initial ideal, okay? And remember, we do that because the initial ideal is simpler to study because it's a monomial ideal. And in this case, the initial algebra is simpler to study because it's a monomial algebra. Furthermore, many properties of the initial algebra pass to the algebra itself by a deformation argument, which is analog to the one of Grover basis theory. However, unlike the case of ideals, the initial algebra is not always finally generated. And this is the big problem in this subject, because there are examples even of 4 generated K algebras whose initial algebra is not finally generated. Okay, now I want to give the definition of Sugby basis. A set of elements, AI, is a Sugby basis of A if the initial algebra of A is the algebra generated by the initial term of the AI, okay? This is actually the analog of Grover basis. And even if the Sugby basis is not finite, it is a system of generator of A. Now assume that A is a finite Sugby basis. Then the initial algebra is an associated graded ring of A with respect to suitable degree filtration. In particular, the initial algebra is a special fiber ring of a flat 1-parameter family whose general fiber is exactly A. This deformation theory aspect was first described by Sturfels. Now, the first one that actually applied Sugby basis theory to the Rees ring, to the study of Rees ring, were Conca, Herzog, and Valla in '96. And we follow, this is a fantastic paper, and we follow actually their lead. Most of what I say is from there. And first, let me tell you the facts that they describe and prove in the paper. That first of all, the initial algebra is, if the initial algebra is Come-Coli, this is due to the deformation, obviously, to this fact. If the initial algebra is Come-Coli of dimension D and type T, then the algebra itself is Come-Coli of dimension T, D and type at most T. In particular, if the initial algebra is Gorested, then the algebra is Gorested. Then, if the initial algebra is normal, then A has rational singularity in characteristic 0 and is F rational in characteristic P. A way to see that is that the initial algebra, this is the fact that it's simpler, is an affine semigroup ring. So by Oxter, normality implies that it's a direct summand of a polynomial ring, okay? And now if you use Buteau, the initial algebra has rational singularity. So by Elkick, it has A as rational singularity. Okay, in characteristic P, it's a little more complicated. You have to use work of Oxter-Uneke to see it. Now, if the algebra itself, A, is a positively graded K-algebra, then you can write it always as a direct sum of AI a K-vector space. And then the initial algebra is also a positively graded K-algebra. We can consider these guys, the initial of AI, what they are. They are the K-vector space generated by the initial term of A, where A is an element in AI, and they're all finite dimensional vector space. And their direct sum give us the initial algebra. Okay, this actually is true even if one does not assume that A is a finite Sugby basis. Okay, now from here you get immediately that the Hilbert function of this and this are the same. Okay, now notice another fact important. If in addition to be graded, you know that the initial algebra is generated by form of the same degree, so the Sugby basis is given by this form of the same degree, then we know much more. We can even, by the work of, again, Conca, Herzog, Valla, we can even see that the H vector is the same. So the multiplicity is the same, the A invariant is the same, and if they are Come-Coli, the regularity is the same, and if the tau respects the degrees, we also have that if the initial algebra is Koszul, then the algebra is Koszul. Okay? Recall that a standard graded K algebra is Koszul if the residual field K you think of it as A over A plus, as a linear resolution over A. Causalness as an analogous characterization as a polynomial, as the characterization of polynomial ring for finitely generated K algebra, in the sense of the celebrated theorem of Auslander-Buchs-Monsell, because that theorem says, remember, that A is a polynomial ring if and only if the projected dimension of the residue field over A is finite, if and only if the projected dimension of every finitely generated A module is finite, okay? If and only if the causal complex over the homogeneous maximal ideal of A resolves K, which by the way is a linear resolution, okay? So in an analogous fashion, substituting the regularity over A to the projected dimension over A, Avermov, Eisenbach, and Piva characterize causalness using the regularity. And they prove that A is causal if and only if the regularity of the residue field over A is finite, if and only if the regularity of every finitely generated graded A module is finite. Notice that every causal algebra is generated by quadrics, but this is not sufficient. However, what's sufficient to get causalness is that the defining ideal of the algebra has a Gromberg basis of quadrics. We often call it G quadratic. Now, let's go back a second to the Rees algebra. As I said, Conca, Herzog, Valla were the first to apply all this theory to Rees ring. So if you assume that I is an ideal generated by form of the same degree, and you have a term order on R, you need a term order on RT, because the Rees algebra is a subring of RT. So you extend it to a term order on the polynomial ring over T in a trivial way. Take U, take V, monomials in R. You want to say what it means that U times T to the I is strictly less respect to I prime to V T to the J. And this is if and only if either I is less than J, okay, or I is J and then better be that the monomial U is less than V with respect to tau. Now, we can consider the initial algebra, if we want to study Rees algebra via Sagby basis, of the Rees algebra with respect to tau prime. And this is the direct sum of, you have to take the power of the ideal, remember the Rees algebra is defined by the powers of the ideal, and take the initial ideal with respect to it. And you take the direct sum, okay? This is very, very important. Now, this is the initial algebra, and inside it, you always find the Rees algebra of the initial ideal. How do you get that? Because the initial ideal to the power I is contained always on this, on the initial of the power. So you get a containment. And this containment is a quality if and only if the initial ideals are equal. Now you would have to check this for every I. However, by the work of Conca, Herzog, Valla, it's enough to check it up to the relation type of the initial ideal. And remember that the relation type of the initial ideal was just what I defined before. It's the largest T degree of the generator of the defining ideal. It's almost time to do the break. I have only 2 minutes and then I'll do the break. I would like to say that, so we just have to check this up to the relation type, and then they get the quality on the Rees algebra, which is the initial algebra. The initial algebra of the Rees algebra is the Rees algebra of the initial ideal. Okay, in the case of maximal minor, this was proven by Stumpfel for the Plucker algebra, and by Conca for the Rees algebra. I want to finish this part because then the next part, which will be a little shorter, is the work with the birds, and it will be shorter. So let me just tell you the last thing I need for the last part. And this is actually a criterion for a set to be a Sagby basis due to Stumpfel, and actually tells you how the defining ideal of an algebra and the initial algebra are related. So the algebra, again, I think of it as a subalgebra of the polynomial ring generated by F1 Fs, okay? And I take a term order on R, on the polynomial ring R, and then I take the initial term of all the Fi. These are just monomial. so are the product of the xi with some exponent. And these exponent vectors, there are s of them, p1, ps, I can make a matrix out of it, okay? I'll call it B. Now we consider two rings. The ring A, we write it as a quotient of a polynomial ring, like I did before in the first part of the talk many times, and I call J the defining ideal. So I send each new variable t to the f's. But I can consider also the algebra, the monomial algebra, defined by the xbi, xb1, xbs. I'll call it A prime. I don't know that this is the initial algebra. However, it's defined by a toric ideal, J prime. And now I take a weight vector. Okay, this just means you give some degrees to the x's, okay, to all the x's, represented though tau for the phi's, which means the initial respect to the w has to be the initial respect to tau of the phi. And then you can extend this weight vector to all the new polynomial ring by just taking the weight given by B transpose times W, because you just, HTI correspond to the minor XBI, I mean the monomial XBI. This XBI is obviously a weight, and that's the weight you give to TI. And then the characterization is as follows. F1Fs is a sub-B basis for A, if and only if the initial ideal with respect to this weight is J prime, is the toric ideal. Remember, there is always one inclusion, but it's actually equality, gives you sub-B basis. And this is not a monomial in general, obviously, because this is a weight. And every reduced Grover basis of J prime will always lead to a reduced Grover basis of J. Thank you very much. Sorry, this was very long for you, 50 minutes. We can take 2-3 minutes break, and then I can do the second part. All right, so since it's time, I'll start, the last part of the talk. And thank you so much. So I know it's hard to stay 1 hour and a half. So this is the work done with the 6 women that I mentioned at the beginning. And as I mentioned at the beginning, I would go also in the direction of consider maximal minors of non-generic matrices, in this case of sparse matrices. So I consider X a 2 by n sparse matrix, and the entries of X are either 0 or variables. So for example, this is a sparse matrix, okay? Now, sparse matrices are very important also in applied mathematics, where we can have lots of information to send, and we have to decide which one to delete, in which place to put zeros, and still give most of the information. Or for example, are very important in data science or in also machine learning, when you have a huge amount of data, and again, you have to select the one that is important. So in commutative algebra, they were first studied by Giusti and Merkel. And this was for actually not 2 by n minor, but for m by n sparse matrices. I call I the ideal of maximal minor now. And Giusti and Merkel investigate the commutacoliness, the primeness, and codimension, and they prove that it depends only on the perimeter of the largest subrectangle of 0 in X, okay? Butcher, in much later, 30 years later, in 2013, studied them again and studied their minimal free resolution, and actually proved that the minimal free resolution is a direct summand of the Igor-Norcott complex that we already saw resolve the generic one. And it can be obtained by the Igor-Norcott complex by a pruning algorithm. Actually, in particular, Butcher proved that the projected dimensional regularity do not change from the generic case. Now, he also proved that the maximal minor form a universal global basis for I, which means that respect to any term order that you consider, the maximal minor are actually a global basis for I. Now, without loss of generality, we can always, because we have a 2 by n matrix, we can always change row and column and assume that our matrix is made of 3 blocks. The first block has size R and has 0 in the second row. The second block is completely generic, and the third block has size S and has rows a 0 in the first row, okay? So we can always assume that R is bigger than equal than S. And actually we can assume that R is positive because the 0 case is the one we discussed in the first part of the talk, okay? Now we want to study the Rees algebra and the special fiber of I, and we want to do it like Conca, Herzog, Valla via Gobler basis and Sagbe basis theory. And so we have to study the initial ideal of I. So I is the 2 by 2 minor of this matrix. So to have 2 by 2 minor, I just need to select 2 column, as I said in the first part of the talk. This is the minor ij, and I call it Fij. So ij are 2 columns between 1 and n. And again, R is the polynomial ring in the variable xij, the entries of the matrix over the polynomial ring K, all over the field K, sorry. And now I want to look at the initial ideal of I, and I choose a diagonal term order. Maybe I didn't explain this before, but the diagonal term order is a term order that selects the element in the diagonal. Now, in our case, a lot of if R is large, a lot of the generator of I are already monomial, like these are all monomial already, and these are also all monomial, but the one of the generic part are not, are binomial, and we would select the diagonal, and that's what means diagonal term order. And by Butcher, choose the initial ideal of I is you just have to look exactly at the term, the initial term of the minors, okay? So only the minors. And for this reason is generated by 3 sets. The first set is the set that you get by multiplying the variables in the first block by this variable of the second and third block. The second set is the one that you obtain multiplying the variable of the third block by the variable up here, and these are already monomial in the ideal I. And the third one is the one that you get by now taking the initial terms of the minors of this generic block, which were binomial obviously in I and are monomial here. Okay, this is a square 3 monomial ideal generated in degree 2. So we can associate to it, it's actually called an edge ideal. We can associate to it a graph. How do we do this? How do we think about it? Think about a graph. The vertices are going to be the variable appearing in the matrices, and the edges are exactly the, so a generator of the initial ideal x1i, x2j is an edge of the graph because it connects the vertex x1i with x2j, okay? And much more this, in our case, this is much more than just an edge ideal, is the edge ideal of a Ferrer bipartite graph. What is a Ferrer bipartite graph? So let me define it now. A Ferrer bipartite graph is a graph on 2 distant set of vertices, V, let's call it V1, Vn, W, W1, Wm, that can be described by a partition. This partition is just a sequence of integers, okay? In our case, there are n integers, as n here, the number of vertices of V. The first integer is m, like the m here, okay? And they're all positive, and they are weakly decreasing, okay? So lambda 1 is less than equal to lambda 2, and until lambda n. And what do they represent, these integers? And why they describe the graph? Because m means that the vertex V1 is actually connected to all the vertices of W. And so there are m edges starting from V1. And lambda 2 is the number of edges that starts from V2 and connect V2 to the first lambda 2 vertices in W, okay? These are order sets. And the fact that lambda n is positive means that the edge Vn W1 is in the graph, okay? So let's look at this in our situation. Before, let me tell you that to every partition, you can always associate, as Claudio did, a Young diagram or Young tableau. And in this case, it's called a Ferrer diagram. So how is made? They will have as many rows as many lambdas you have. So n rows in our case. And the first row will have lambda 1 boxes, n boxes in our case. The second row, lambda 2. And the last row, and lambda n boxes, okay? Now, let's go to our particular case, to our initial ideal, which is an edge ideal. Is a Ferrer ideal, because the edge ideal is Ferrer bipartite graph. So I have to tell you what are the vertex sets, okay, and what is the partition. The vertex sets, as I said, are V, which are exactly the variable appearing in the first row in the correct order, and W is the vertices appearing in the second row in the opposite order of the matrix. And the partition is n minus r, r times. Why is that? At least if r is bigger than 0, because look at this block. This is exactly size r, and each one of these variables is connected to all of them because you have all these minors. So you have all this monomial, and so there are these edges, and these are exactly n minus r of them. And that's why we have n minus r, n minus r, n minus r, r times. And then this one again, sorry, is connected not to this one, but all the one below, which are exactly n minus r minus 1. And this one is connected to all this, which are n minus r minus 2, and so on. And the last one is connected to all this, which are exactly S, because this is block S. So this is a lambda n, in our case is S. Now, I said I can assume r bigger than 0, and this is true if r is bigger than 0. The Ferrer diagram will be exactly what I described. I have to take the first row, we'll have n minus r boxes, and so on. Each of the small, you don't see the boxes here, represent exactly a, if you want, an edge, and represent exactly, in our case, a generator of the monomial ideal, of the initial ideal we are looking at, okay? And these are exactly the generator that we call S1. These are the generator that we have called before S2. And these are the generator that correspond to the generic part, taking the initial term of the generic part of the matrix. That's why there is the staircase kind of diagram. Okay, now I want to do an example to be more clear. Okay, so we take the example, the block R here is 3 and S is 2. This is the generic block. And now I is the 2 by 2 minor. This is the Ferrer ideal associated to lambda. Here you multiply this x11 times all this variable, and there are exactly 6 of them. x12 times all this, and there are exactly 6 of them. And then when you take x14, remember you are taking always the diagonal term order, so you get all this, but you don't get this, and that's why there are 5 here, and so on. And this is the Ferrer diagram in this example. And as I said, each one of this represents the generator x11 times x29. Okay. Now, let me tell you, every time you have a diagram of this kind, you can actually associate to it what's called a ladder. So in this case, we can actually associate 2 ladders. So what are ladders? Ladders are a subset of a matrix that have a shape which is like a staircase on the bottom, like this, and a staircase they can have on the top. When they are like this in the top, they're called one-sided ladder. So how do you assign a ladder to a diagram? Well, you just fill up all the boxes with variables. So we are going to fill up these boxes with variable. And which variable do we put? But we add new variable. We create a new polynomial ring like we did before, and we take the new variable Tij, and we associate it to the generator x1i, x2j. So we put here, for example, T19, here T18, here T17. And so this is the ladder. One-sided ladder we call L lambda. We also have another ladder that is going to be very important, that is two-sided. You see there is a small staircase here, where we actually, these are just, they're not part of the ladder, they're just indices, okay? They are placeholder. Instead, here they are part of the ladder. So this ladder is made like this. We also put the variable of the appearing in the matrix, the variable of the polynomial ring R. Here, actually, the one that appear in the matrix in the first column, and here the one that appear in the second column, in the reverse order that I explained before. This is very important. You are going in the reverse order. If you look at the matrix, I'm going in the reverse order, okay, for the second. Okay, now I want to describe, I said, using Sagby basis, the Rees algebra, all right, and the special fiber of this monomial idea, okay? And so to study them, I want to consider two polynomial rings and map into it. So the polynomial ring, like before in the first part of the talk, will be called S, that is mapped to the Rees algebra. I call this map rho for Rees algebra, and this map Phi for special fiber. Here again, we'll have the polynomial ring T. The polynomial ring S consists of the polynomial ring over K of all the entries of this ladder. And the polynomial ring T consists of the polynomial ring over K of all the entries of this ladder, okay? And we send, like we did in the first part of the talk, the Tij to the generator x1i, x2j, t, and the Tij for the fiber to the generator x1i, x2j. And we want to know lots of things, like before, the same thing, the same property that I point out for the Plucker algebra and the Rees algebra of minors. We are very lucky because by ladder determinantal ideals, Ferrer ideals, and edge ideals, and blow-up algebras have been widely studied. I just mentioned some names that I need. For example, there is work of Narasimha, there is work of Chung, there is work of Conca, Villarreal, that introduced the name edge ideal, Cmas, Vasconcelos, Villarreal, Onaga, that describe the blow-up algebra of Ferrer ideals. So we can put all this work together and describe this special fiber and the ring and the Rees ring of this monomial ideal. And this is the theorem. So what do we say? First of all, the defining ideal of the special fiber ring is the ladder ideal, the 2 by 2 minor of the ladder, the one-sided ladder, L lambda. The defining ideal of the Rees ring is the 2 by 2 minor of the extended, the two-sided ladder L lambda prime. 2 by 2 minor of L lambda prime in lambda. What does it mean a minor if you have a ladder? You just have two the minor that are actually defined, okay? And from this is obvious that the relation type, since our 2 by 2 minor, is 2, okay? And then we furthermore see that the Rees algebra is normal. And since it's a monomial algebra, is actually has rational singularity in characteristic 0, and is a fraction in characteristic P, so is actually Comecoli. The special fiber ring, once we know that this guy is the Rees algebra has rational singularity, this is a direct summon. So by Buteau also has rational singularity. So it will be normal in Comecoli. And furthermore, we know its dimension. I mean, the dimension of the Rees ring is always the dimension of the ring plus 1. But the special fiber, the dimension of the special fiber is a very important invariant called the analytic spread. And in this case, is the minimum between 2n minus 3. This is actually the same number as the generic case. I had pointed this out in the case of the Grassmannian. And 2n minus r minus s minus 1. This is actually the dimension of the ring R, is the number of variables in the matrix minus 1. Okay. And then with respect to the diagonal term order on the two ladders, the generator of the 2 by 2 minor of either ladder form a Gromberg basis for the defining ideal of the Rees ring and the special fiber. So as I point out in the second part of the talk, they are G quadratic. They have a Gromberg basis of quadrics for defining ideal. So the Rees ring and the fiber ring are causal. Okay? So now, how do you prove this? I almost explained everything. I just should say that part 1 is due by the work of Corso and Nagel, and then part 2 is due to Raphael. He proved that for every edge ideal, the initial ideal is of fiber type. So now, remember, fiber type means that the defining equation of the Rees ring are obtained immediately from the one of the special fiber. So since the equation of the special fiber are the 2 by 2 minor of the ladder, we just have to add the linear equation, which were just the equation coming from the syzygy. But this is a monomial ideal. It's easy to describe the syzygy. They come from reduced causal relation. And so they will really correspond to just taking the minor of the extended ladder that involves either the first column or the first row. So any minor that contains the first row. Okay, so L is generated by, the kernel is generated exactly by the 2 by 2 minor of this extended ladder. Now, to prove 4, the normality of the Rees ring, you have actually 2 ways to do it. One is using Cmas, Vasconcelos, Villarreal, because they actually characterized edge ideals of graph that are bipartite as the only edge ideal of graph whose Rees algebra is normal. Or you could use the work of Conca that prove that ladder determinantal ideal are normal. And for the dimension of the special fiber, you can either use Corso-Nagel or actually the work of Conca that did it, okay? And then for 6, you can use the work of Narasimha. So this, now that we are in a good position because we described the Rees algebra of the initial ideal, and we want to study the Rees algebra of I and the special fiber of I, and we would like to use Sagby bases. So we have to extend, as I explained before, tau to order on RT that we call tau prime, and we ask, is the Rees algebra of the initial of I that we describe in this theorem equal to the initial algebra of the Rees ring? If this is correct, we can use all the machinery that I developed in the second part of the talk to actually deduce property for the Rees algebra of I and for the special fiber ring, as we'll see. Now, in general, you have to prove the quality of all the power. The initial ideal of all the power is the power of the initial ideal. But by Conca, Herzog, Valla, I just have to prove it up to the relation type of the initial ideal. And the relation type of the initial ideal is 2. So I only have to check this thing. This equality will do it. How do you check this equality? You have to, actually, you just do it with Hilbert functions. And the way you do it is, you have an inclusion of these ideals. But this is the initial ideal of I squared, so it has the same Hilbert function as I squared. So to show that these 2 are the same, I just have to show that they have the same Hilbert function. So I have to prove that the Hilbert function of the square of the initial ideal is equal, because of this, to the Hilbert function of I squared. And I don't compute this Hilbert function, I just compare them. I use induction on N. We assume that R is positive because Conca had the result, in any case, in the generic case, in the 90s. So I take I1, the ideal generated by the entries in the second row of the matrix. So this is just an ideal of generated by variables. And I2 is the ideal of the 2 by 2 minor of the matrix obtained by deleting the first column of X. And this is a monomial ideal. I can write I, because R is positive, as this monomial idea plus this, the maximal minor of this, the other part. And I can also write the initial ideal, that this monomial ideal state, plus the initial ideal of I2. And then I can take their powers, and these two by induction have the same Hilbert function. So to prove that everybody, these two have the same Hilbert function, I just do some short exact sequences. So I never compute it, I just compare. And I get this equality, which is give me finally this beautiful result by Conca-Herzog-Walla. And now we want to use this to apply to our Rees algebra. And we get immediately that the x's together with the minor time t, the Fij, which are the 2 by 2 minor, is a Sugby basis for the Rees algebra. Also, we get that the Rees algebra has rational singularity in characteristic 0, okay? Because the initial algebra has this property. By we saw that the initial algebra has rational singularity, so you can use Elkic, for example, or Conca-Herzog-Walla. Once the initial algebra has it, the Rees algebra has it. And then the Rees algebra is a Koszul algebra, and again, as we saw, this pass from the initial algebra to the algebra. And as I mentioned at the beginning, if there is algebra has good property, we can deduce good property about the powers. Because Bloom shows, for example, that if there is algebra is a Koszul algebra, then all the power of I have a linear resolution. So they have the regularity of the power is the smallest possible, 2L for all L. So this followed by Bloom, okay? Now we wanna spend the last 10 minutes to explore the defining equation of this two ring, of the Rees ring of I and of the special fiber ring of I. So again, I map to the same polynomial ring that I used before, that I mapped to the Rees algebra of the initial. I map it to the Rees algebra of I. Send the Taj now to Fijt before I send it to the initial of Fijt. This map, I can call it rho instead of rho prime. And the defining ideal, I'll call it the kernel, I call it J, like I did in the first and second part of the talk. And then I can map to the special fiber ring, the polynomial ring T. Again, these are just the polynomial ring over K, whose entry are generated by the entries of the ladder L lambda and the two-sided ladder L lambda prime. And I call the defining ideal of the special fiber ring, I call it H. Just to make our notation easier, I refer to the variable that are actually not present in IS and T, just to make it easier. So, but the identification is that this variable are 0. So the x, y are always 0, remember, if u is in the second row and in the first block of the matrix, or if u in the first row in the last block of the matrix. Or the Tij is 0 if I and j are 2 column in the first block of the matrix, or if I and j are 2 column in the last block, the third block of the matrix. Now I want to remind you the two ideal that I defined in the first part of the talk, the Blücher ideal and the linear ideal. These were the ideal that generate together the defining ideal of the Rees algebra of 2 by 2 minor of a generic matrix. And now what I want, I can think of these two ideals inside my S and T with this identification. Obviously, some of this variable will be 0, but these are still living in S and T. And actually, it's very funny because you could have in general that two of these are 0 and you get a monomial, but this never happened because we want that this P ijkl and lu ijk together, they define exactly they generate the defining ideal of the Rees ring. So they should generate a prime ideal. So you cannot get monomial because the Rees ring is a domain. And in fact, our theorem says that the defining ideal of the Rees algebra is L generated by L and P, and then immediately we have that the defining ideal of the special fiber ring is the Plucker ideal in this, extended to this ring. And this follows obviously immediately from this, and in particular areas of fiber type. Also, this LUIJK and the PIJKL and the PIJKL are a Grober basis for J and H respectively. So the way we prove this, we have to use the last part that I said that was due to Sturmfeld, at least I studied it in the Sturmfeld book, and we take a suitable weight, W. A weight means, as I said, giving degrees to the variable of the ring R. So we are the variable appearing in the matrix. So I tell you what the degree matrix is. We give degrees 1 to every variable that appears in the first row, and we give degrees J to every, 1, 2, 3, and to every variable that appears in the second row, we give the degree of the column, okay, the corresponding column. This weight actually extend to T and S, exactly like Sturmfeld did, because you can give the weight of T ij the same weight that you give to the initial term of Fij, which is x1i, x2j. So the weight of Tij will just be j plus 1, because this is weight j and this is weight 1. And now, so this is when in all T and all S, and this weight represents tau, since the initial form of Fij respect to W of Fij is exactly the initial term of Fij with respect to tau. It's easy to see. So because of that, okay, using Sturmfeld, we get immediately that the initial ideal of J is the 2 by 2 of the extended ladder. This is because we knew that it was a Sagby basis. And if it was a Sagby basis, we knew the initial algebra is the Rees algebra of the initial, and this is the defining ideal of the initial algebra of the initial, of the initial algebra of the Rees algebra. So, and as I told you, that's the way that the two initial ideals are related. And I mean, the two defining ideals are related. Now, we want to prove that J is generated by L and P, but L and P are containing J. So it's enough to show the quality that they have the same initial ideal. So since we know the initial ideal of J, it's enough to prove that the initial ideal of L and P is exactly the 2 by 2 minor of the extended ladder. And to do that, it's enough to show that each 2 by 2 minor of the extended ladder, the two-sided ladder, L lambda prime, is the leading form with respect to W of either a PIJKL, the generator of P, or LUIJKL, the generator of L. And then 3 follow directly from Sturmfeld, as I point out before, the Grober basis lift. And you knew already that the generator of this guy were a Grober basis for it. So now we have immediately a corollary from here. Actually, it's funny. One tells us that the initial algebra of the special fiber ring is actually the special fiber ring of the initial algebra, and that you have to use Sturmfeld again, but on the opposite direction. Because by the first part, now you know that the defining ideal of, you remember, you know that the initial ideal, the initial ideal of the defining ideal of Fi is exactly the defining ideal of this guy, okay? And that's why you get the quality. Okay, so now, so you use the opposite direction. Now, I would like to mention why the other are correct. Why the other follow. These follow immediately, as we said before, but we could even use just that there is ring. Is because actually you can just use for this one that part 3, that these are Grobe bases, as I said before, because G quadratic. So this follow right away. We already mentioned this many times. This follow because, for example, Ri is rational singularity, characteristic 0, or this is a normal algebra. You can use either of the two proofs, as I mentioned already many times. And now this is important. Why does this follow? But I told before that by Conca, Herzog, Valla, if the initial algebra is Goresten, then the algebra is Goresten. So we have to just look when the initial algebra is Goresten. And the initial algebra is Goresten, so you have to look when this algebra is Goresten. And this is a ladder determinantal ring. So this was described by Conca. So using this characterization, you can prove this. Or you can use the Corso-Nagel that did it for Ferrer ideal, because this is a Ferrer ideal. Also, the regularity can be computed again, because I said that once they're Come-Coli, we can compute the multiplicity, everything, the A invariant, everything passed from the initial algebra to the algebra. And all these invariants were computed for the special fiber ring of Ferrer ideal or for ladder determinantal. So for example, from the work of Corso-Nagel, we can compute it for this ring, and then we can transfer it to f of I because of this equality and the work of Conca, Herzog, Valla. So we get that the regularity is n-3, the minimum of n-3, which is the one in the generic case, or n-r-1. I remind you, r is the number of zeros in the second row, was the largest of the two. And there are many other properties that you can pass, but my time is off. So I just want to finish telling you that we conjecture that the same results are valid for any m, and the difficulties in describing the blow-up algebra of the initial ideal, because it's much more complicated. It's still a square-free initial ideal, but is generating degree bigger than or equal than 3, and much less is known. For example, for degree 3, there is work of Lin and Shen, recent work, where they study the blow-up algebra of three-dimensional Ferrer diagrams, but they assume that they have a projection property, which means that if you slice it, you know, each slice is a Ferrer diagram, but and a slice has to always, you know, sits on top of the previous one. And the 3x3 minor of a sparse matrix, the initial ideal of a 3x3 minor of a sparse matrix, unfortunately, don't have the projection property. So I would like to stop here and thank you very much for your attention.
Thank you very much, Claudia. If there are any questions, I guess you can either post them, or there'll also be an opportunity at the tea room. I did post a link to the tea room and the password in the chat session.
Okay. Yeah, I have ready to go for when they're done.
Okay, very good. Any questions? I don't see any in the chat, so maybe there'll be some questions when we meet for tea. Oh, there's David, he's back.
I'm actually back, yes. And I did have a question. There's, of course, a classification of 2 by n matrices of linear forms, which includes lots of other matrices besides these. Sorry?
Yes. There is the work that you did, for example. Yes.
Yeah, well, and goes back to Kronecker, actually.
Yes.
But I believe Alessio did something with Rees algebras of those. Do you know what exactly the status is? Did he compute the ideals of generating relations? Or did you or someone else?
Sorry, I still.
So if you take one of those other kinds of 2 by n matrices of linear forms,
Yes.
do you know the Rees algebra? Do you know the ideal of the Rees algebra in that case?
Yes. If I know it. I don't. I didn't look at it. No, I don't. Sorry. You asked if I know it. I thought you knew it. No, I don't. No, I don't.
I thought that Alessio had proved something about them. But
I mean, he proved it in the case, for example, he did the case of rational normal scroll. So if you consider the 2 by 2 of, if you take the rational normal scroll. So obviously they have a particular shape. And there is some other work, but Betty definitely did, Alessio. It's a beautiful paper where he uses, global bases, and they found a particular order because Conca, Herzog, Valla actually use Sagby bases to do the work for rational normal scroll, but when they're balanced. So every block is almost the same size. But they couldn't do it because in that case, the initial, that's where we took the inspiration. The initial of the Rees algebra is the Rees algebra of the initial. And they study actually the Rees algebra of the initial, and then they are able, once they have the initial algebra, they are able to lift it exactly like we did, okay? But they cannot do it for every rational normal scroll. They do prove there are Cosy and they have linear powers, but they couldn't find the equation. And it was Alessio that found a particular order, actually, a very particular order for which the equation are actually still Cosy and they could do the work. So use global basis theory, compute the multiplicity, and there's some generalized catalytic number. It's a beautiful, beautiful paper, yes. But in general, I don't know. Besides this, I don't know. I think it's very difficult in general.
There are more new messages. Wait. Thank you very much.
Yeah.
Yes. Good.
You're welcome to everybody. Thank you very much to have listened. It's so difficult, I know. I'll try to open the Theorem. I never went, so I don't know how it works really. But after this, I'll go to the Theorem.
Okay, good.
Thank you, Claudia. Nice talk.
And thank you guys really very much to organize this seminar. This is such a work.
Really enjoyed it.
Really good. Thank you so much.